dorks of yore.
Hey guys, I'm Pat Kilbane. Welcome to RPG Science, where we explore the physics and biomechanics behind tabletop role-playing games. Today I thought it would be fun to take a look at the Maul, a thuggish weapon popular with strong and brutish creatures of all stripes. In particular, we'll figure out how fast it swings and how hard it hits. Since we're talking about the acceleration of rotating objects, the first physics principle we need to explore is moment of inertia, which is represented in equations by the letter I and units of kilogram meters squared. The moment of inertia of an object tells us how resistant it is to changes in angular velocity about a particular axis of rotation. In other words, how hard is it to swing? So let's take a look at how hard it would be to swing this 5th edition Maul, which the player's handbook says weighs 10 pounds or 4.5 kilograms. Moment of inertia can be complicated to calculate because it depends upon the distribution of the mass throughout the object. But as a general principle, moment of inertia is proportional to the mass times the square of the distance of that mass from the axis of rotation. If we were to take this Maul and double the mass of the head, that would double its moment of inertia. But if we were to double the length of the handle, that would quadruple its moment of inertia. So all the heavy-hitting weapons like axes, hammers, maces, they're going to have higher moment of inertia because their mass is concentrated a greater distance from their axes of rotation. Let's break down the Maul starting with the haft, which we will say is 1.1 meters long and 0.032 meters in diameter. By calculating its volume and multiplying that by the density of ash wood, we end up with a mass of 0.66 kilograms. We'll use this formula for the moment of inertia of a uniform rod rotated about its end, which gives us a result of 0.27 kilogram meters squared. Now let's tackle the head of the Maul. Since we know the mass of the haft and the overall mass of the weapon, simple subtraction gives us a mass of 3.84 kilograms for the head. We can estimate the head to be positioned about 1 meter from the axis of rotation. So our simple moment of inertia formula of I equals md squared gives us a value of 3.84 kilogram meters squared for the head. When we add the values of the haft and the head together, we get a total moment of inertia of 4.11 kilogram meters squared for the entire weapon. And I know what you're thinking. That's great, Pat, but what am I supposed to do with that? Fortunately, sports scientists have come up with a formula for using moment of inertia to determine swing velocity. This particular formula is for a two-handed swing from a major league power hitter, and with a Maul in his hands, he generates an angular velocity of 20.5 radians per second. Since the Maul's head is exactly 1 meter from the axis of rotation, its linear velocity at impact is 20.5 meters per second, or 46 miles an hour. And on impact, the peak force generated will be about 32,000 pounds. We might extrapolate from our experiments in episode 7 that 32,000 pounds of force would translate to be about 4d8 points of damage. But all that hitting power would come at a price. The amount of time it would take for that Maul to cover its 100-degree arc of swing is 170 milliseconds. This bastard sword, with a much lower moment of inertia, takes only 90 milliseconds to cover that same angle. We could say, based on our experiments in episode 2, that the bastard sword's 80 millisecond advantage would give it a +4 hit bonus against the Maul for weapon speed, or perhaps a -4 for the slow and cumbersome Maul. In 5th edition, the Great Weapon Master feat allows you to take a -5 hit penalty to gain a +10 bonus to damage. So looking at this information about the Maul, it's interesting to think about a particular weapon giving you that same kind of trade-off. Might be kind of cool. That's all for now. School your friends on moment of inertia, have fun at the game table, and I'll see you guys next time.